In the previous video, we talked about resistors in series and resistors in parallel. We studied the relationship between the current and voltages for all the respective individual resistors for the series circuit arrangement and also the parallel circuit arrangement. Now I move on to talk about another very similar concept, very practical concept that is used quite often, similar like how you deal with series and parallel circuits. This is on potential divider. Okay, so the word potential divider, we have to understand that literally it just means potential difference being divided. Okay, so this is potential difference. We are not talking about potential energy. We are just talking about potential difference, not potential. Okay, this is potential difference. So the potential difference is being shared or is being divided. Okay, so who is it divided to? Later we look at the circuit below to understand the whole situation in greater detail. Okay, so right now I'm giving you a very simple circuit over here. You have a series circuit as you can see over here. So this series circuit consists of a power supply which is 6 volt and is connected in series to resistor 1 which is 1 ohm and resistor 2 that is 2 ohm. And resistor 1 and resistor 2 are both connected in series. Later we want to study the voltage across resistor 1 and also the voltage across resistor 2. These are the two things that we're interested to find because in this topic we're talking about potential difference, right? So our interest will be the potential difference across R1 and also the potential difference across R2. But before we go further, I would like to say that if you measure the potential difference encapsulating both R1 and R2 inside it, you get voltage 1, 2 actually, and this voltage 1, 2 is the combined voltage of voltage 1 and voltage 2, which will also be the voltage across the battery as well. That's why I write it as voltage across the battery. Okay, so because this is a series circuit, based on our understanding from the previous video, we know that resistors in series, right, their current should be the same. So since R1 and R2 are connected in series, okay, therefore we can come up with a statement by saying that I1 will therefore be equals to I2, and because it's equals to I2 will also be equals to I12. This is what we have discussed in the previous video based on our understanding of series circuit. Okay, so based on this understanding here, we can actually derive some new equation which will be quite interesting to understand the idea of dividing potential. Okay, so let's say we focus on the potential difference across R1 over here, which is V1 over here. If you're interested with the resistor over here, can we just ignore R2 right now by saying that I1 will be equals to I12? It's still valid, right? I can say that I1 is equals to I12. Okay, because right now my focus is on R1, my focus is not on R2, so I can just say that I1 is equals to I12. I'm not saying anything new, I'm just choosing the focus on R1, I'm neglecting R2. Okay, the whole equation still makes sense, I'm just removing one element from it because that's not my focus. Okay, so I1 is equals to I1 is equals to I12. Okay, based on Ohm's law, okay, or the definition of resistance, depends on how you want to see it. This I over here is actually just V over R, right? So we learned before that the subscript must be kept constant. So if this is I1, it will be equals to V1 over R1. Whereas on the right hand side, if you change it to become V over R, this one will be V12 over R12. Okay, once you reach this point already, right, we can make a bit of interesting adjustment to see how everything works. But the first thing I want to do is I would like to rearrange it a little bit by bringing the, let me use other neutral color, bringing V12 to the side. And now the equation will be V12 on the side. But because V12, as I mentioned earlier, if I just encapsulate both R1 and R2 together to measure across them together, you get V12, right? And V12, as you can see over here, it should be the same as the voltage across the battery. Because even though I'm encapsulating R1 and R2 inside this green measurement of voltmeter, you can see on the other side is actually covering the battery. On the other side is covering the battery, so that means that it is actually also measuring the voltage across the battery. So here I can write it as V12 is acceptable, and I can also write it as V battery. Okay, sometimes you also call it as V input. Okay, so that's the first thing that I do. The second thing that I do is I would like to expand R12. Okay, what do you mean by expand R12? I know that R12 is a combination of R1 and R2, and because R1 and R2 are in series, we can just combine them by a normal addition, right? So that's why R12 is just R1 plus R2. Okay, so that's the second thing that we do. Okay, this should be in dotted line. The last thing I'm going to do is I'm going to shift the R1 to the right hand side. So I'm going to shift R1 to the right hand side. So if I shift R1 to the right hand side, it'll be above the fraction, right? So I put it as a numerator over here. And this will be my final equation. Okay. Later on, we'll try to understand the structure over here, but I'm just telling you that this is the final equation that I want to obtain. Okay, so this is me focusing on R1. This is the final equation I can obtain. I can also choose to focus on R2. So we will go through a very similar process. And we can say that if we focus on R2, then we are neglecting R1 for momentarily. So this will be I2 will be equals to I12. So I2 is equals to I12. That's why if you break it open, this one will become V2 over R2. This one will become V12 divided by R12. Okay, again, I'm going to do the same three things again. First, I'm going to shift the V12 to the right hand side for a little bit. Oops, using the wrong color. Okay, I'm shifting it to the right hand side. First step. What am I doing? Then V12 is now expressed as V battery. Okay, then I'm breaking open R12. If I break open R12, what we get is R1 plus R2. Okay, because they are connected in series. And lastly, I can shift the R2 to the right hand side. Okay, if I shift it to the right hand side, now R2 will become our numerator, so I put it above the fraction. So now I'm left with V2 is equals to R2 over R1 plus R2 multiplied by V battery. Again, this is the final equation that I wish to obtain actually. So I'm going to bracket it and I will discuss with you the structure of the equation. Okay, so here you have two equations. The first equation tells you that V1 is equals to R1 over R1 plus R2 multiplied by V battery. On the other hand, you have V2 which is equals to R2 over R1 plus R2 multiplied by V battery. Okay, so we have these two equations here. We can actually sort of try to generalize it into a general case. If you try to generalize these two equations, the equation that we will get is, if you want to find the resistor, the voltage across resistor X, you can be equals to the resistance of X divided by resistance total. Okay, multiplied by the voltage input. Okay, so these things require a bit of explanation. So basically, if I want to describe it, I will say that this V input here will be how much energy provided across the series circuit. Okay, whereas this R total over here is who are maybe, because there's many, right? Okay, who are sharing this energy. Okay, so these are the two important things you need to know. How much energy is being supplied to the series circuit? In this case, this is a series circuit. 6 volt or 6 joule per coulomb is supplied across this series circuit. So that's why you put in the 6 volt over here, the voltage of the battery. So the battery is a power supply, right? And it supplies to this series circuit. So that's why you put the input over here as the energy provided to the series circuit. Okay, under the fraction or the denominator of this fraction, I put in all the resistors that are sharing that energy that we mentioned just now. This 6 volt over here is being shared between the 1 ohm resistor and the 2 ohm resistor. So we just add up all the resistors that are trying to share that 6 volt or 6 joule energy per coulomb. Okay, so Rx over here represent what are we interested in. If you're interested with resistor X, then you just put resistor X. If you're interested in resistor Y, then you put in resistor Y, whichever resistor that we're interested in. Okay, then this Vx over here will tell us how much energy received by the resistor of interest. Okay, in this case, my resistor of interest is X. Okay, in this case, it's IE, it's RX. But it can be other cases. You can look at Y, you can look at Z up to the situation. Okay, so this equation here allows you to know if there are that many resistor trying to share a certain amount of energy, which resistor will receive how much energy. Okay, to put it into context, there's R1 and R2 trying to share that 6 volt energy. If I'm interested with R1 receiving how much energy, I put R1 over here, then I get how much energy received by R1. If I put R2 over here, I receive how much energy received by R2 over here. Okay, of course, when I'm saying energy, you have to know I'm talking about voltage over here, because voltage is just energy per unit charge. Okay, so that's the equation that I'm trying to pursue here. This equation here will tell us how do we divide our potential difference. Okay, if you still haven't seen clearly how the potential difference is being divided, let me draw it in the way that we usually do in school. Okay, let's say this is your input voltage. Okay, how much voltage input do you have? Your input voltage for this particular situation here is 6 volt. Okay, so this is the amount of energy, total amount of energy that you have over here. Okay, but you are going to divide the energy. So imagine this is a whole cake over here. You are going to split the cake into two, because a part of the cake will be given to R1, a part of the cake will be given to R2. You know that R1 is less in terms of resistance, so R1 need less energy to pass through. R2 has greater resistance, so R2 will require more energy to pass through. So if this is a total amount of energy that need to be shared, the amount of the energy must be shared completely, right? You know that the charge, when they get back to the negative terminal, there must be 0 joule energy. So that means by the 6 joule energy for every coulomb of charge will need to be divided completely, divided like nothing left, divided completely between R1 and R2. So you know that R1 will receive less, R2 will receive more due to their difference in their resistances. So therefore we can come up with a conclusion by splitting them into two parts. Okay, so one will receive more, one will receive less, right? So it should be something like this. Okay, so the one receiving less will be R1, so I'm going to shade this in red. So how do I know how much is being given to R1? Well, I know that all the energy here will be shared between R1 and R2. So I'm going to say this is actually R1 and R2. Okay, R1 and R2 will take completely that input voltage. The input voltage will be shared completely between R1 and R2. So there's only two people trying to take that energy. Okay, so that's the denominator, because that represents everyone. Okay, this portion here is only in the one that we're interested in, which is R1. So we're going to put R1 on top. So this is the fraction that represents this red portion over here. Okay, on the other hand, if you look at the blue portion over here, this is the blue portion. Again, if we look at the whole cake, which represents the denominator, the whole cake will be R1 and R2 as the denominator, because the whole cake will be shared between R1 and R2, but the blue part is what we are interested in, so that's why up here our numerator will be R2. Okay, so this fraction here represent this portion, this fraction here represent this portion. Okay, so if we multiply by V input, which is 6 volt, okay, so let's say this is 1 over 3, right? So this is 1 over 3. This whole piece of cake maybe 3 kilo, or the whole piece of cake 3 joule or 6 joule energy. So if you take 1/3 of it, 1/3 of it will be 2 joule of energy. So this will be V1. So V1 will be equals to 1 over 1 plus 2 multiplied by 6, so that's, sorry, 2 joule energy, 2 volt or 2 joule per coulomb. Okay, so that means by this 6 volt of cake, R1 will receive 1/3 of it. 1/3 of this 6 volt cake will be given to R1. 1/3 of 6 volt is 2 volt, that's why 2 volt will be given to R1. 2 volt will be divided to R1, whereas the rest, which is the 4 volt over here, will be divided to R2. You can find it using the same way by multiplying it with V input. Then you get the voltage across R2. So you can substitute in, this one will be 2, so it will be 1 plus 2, multiplied by V input, which is 6. So you can see that this is actually 2/3. So 2/3 of this cake, 2/3 of this 6 volt cake is being given to R2. 2/3 of this 6 volt is 4 volt. That means by 4 volt is being given to R2. Okay, so you can see that over here, if you make a measurement, you get V1 is equals to 2 volt. And the blue resistor R2 over here will receive 4 volt. So you can see that 6 volt has been divided completely in between R1 and R2, where R1 receive 2 volt, R2 receive 4 volt. If you add them up, you get back that input, which is 6 volt. Okay, so this everything here should make sense. If you choose to do it using series and parallel, you still get the same answer. Because if you see here, if I want to do it using series and parallel way, I can actually do it as well. I can say that combination, which is V12 is equals to I12 R12. Okay, I know V12 is the battery, so that's 6. R12 will just be 1 plus 2. So I know that I12 will be equals to 3, right? I12 is equals to 2, sorry. Okay, so I know that I1 is equals to I2 is equals to I12. So if I'm interested to find V1 will just be equals to I1 R1. I know that I1, I2, I12 is all 2 ampere. So 2 times 1 will get 2 volt, that's V1. Whereas if I want to find V2, V2 is I2 R2. So that will be 2 times 2, so that will be 4. Of course, this is just using series and parallel, what we discussed in the previous video to solve the same problem. But you can see that all this calculation here can be simplified by using one single equation. If you're interested in R1, this is the equation to use. If you're interested in R2, this is the equation to use, as what being demonstrated over here. Okay, so both methods are actually being used interchangeably. Certain situations, potential divider allows you to find it faster. Certain situation, you might need to go back to all these methods to solve the question. But before we go, right, I would like to mention one thing which is very important, which is if you're using potential divider, you have to understand that all these equations can be proven or can be derived based on the first important statement, which is R1 and R2 are connected in series. That means, but if you want to talk about a potential divider, you have to make sure all the resistors that are sharing the voltage over here, all the resistors that will be dividing the voltage over here, will need to be connected in series. Okay, so if today R1 and R2 is connected in parallel, then this whole thing doesn't make sense anymore. Okay, so potential divider, this concept here can only apply when our resistors are connected in series. But in certain situations, in certain questions, you might see some series parallel combination, and it specifically asks you to use the concept of potential divider. So if there's series combined parallel, make sure you combine some of the resistors until all of them become a series circuit first. Then only you're able to continue or proceed with the concept of using potential divider. No matter what, you have to manipulate your circuit, combine some of the resistor, make it a full series circuit first, then only you can start to talk about potential divider. Okay, so that means that you cannot directly use it in certain situations. You have to try to adjust it to make it conducive to use the concept of potential divider by making it a complete series circuit in the first place. Okay, so that's it for potential divider. Thank you very much.